Any issues? Hello.
No, no, sir.
Okay. So let's continue with the point where we have stopped. We were looking at data-driven model in at last. Okay. Okay. So we were trying to look at the data-driven model. The simplest data-driven model one could think of is the regression model. So simple regression. So you call it linear regression, multilinear regression, or anything, so on and so forth. So the structure of the model would be, okay, output as a linear combination of various input variables. Okay, so your output y, okay, as a linear combination of various input variables. And ideally speaking, this beta node, of course, you call it as bias or intercept, and these are the coefficients corresponding to each of the predictors. And this is the model output, which I call it as y. And you also have, so let's say how do you do a model development? Let's say you have a data, which I keep it in a tabular form, okay? Maybe first column is the number, and you have 1, 2, 3, etc. and samples, okay? You have your input x1, x2, etc., etc., xn, and the corresponding y value. So you have your first x11, x21, and maybe xn1. And y1. And again x12, x22, xn2, y2, all the way around. You have x1n, x2n, or other. Uh, xnn and yn. Okay. So what does that is indicate? Let's say y corresponds. Let's just assume. Let's say you are predicting y the composition. Okay. As a function of various input variables, this could be temperature, this could be pressure, this could be vapor boiler, so on and so forth. So you have a lot of predictors, and you would like to predict the output. And this is, so you do some experiment, or you collect some data from a overall from a system, and you make the table ready. So this is our data table. And what you really need to do is you need to have your output y, beta naught plus beta 1 x1, etc., beta n xn. Okay. So I would now like to call this as y, this y as y predict. So y actual. So this is, you got it from your experiment, which I call it as y actual, and this is the model predicted output. And so your y, the model. So what is your ultimate aim? So what we really need to have your original physically observed value y actual should be close enough to the model predicted value. So because you are trying to model a system fully by means of the data, and you have collected the data and you made them as a table, and you are trying to develop a model of this particular character. Mind it. So this is definitely, there is no first principle coming, there is no mass transfer coming, there is no heat transfer coming, there is no transport equation coming. So your model is mostly what you call as parametric in nature. Parametric in the sense that model structure is kind of prefixed. So this is the overall framework. You can, so the flexibility here is to add how many x's. So it means if there are only three predictive variable, you do it that way. If there are only one, do it that way. You have, if there are n, you do it in that way. So can someone tell me what is the best way to, how do you do it? How do we go ahead? I hope you might have learned this in your MPL courses. Anyone? Anybody, please? In that case, let me ask someone. Ashutosh, how do you do in this particular context? To develop the model, what will you do?
So this kind of equation y is equal to b naught b1x. Like I'll try to draw a matrix and then solve it around.
No, matrix is what? So the matrix is right here. So what should be the guiding principle for the model development? There should be a philosophy, right? There should be a way. I would say guiding principle.
So like the iterations should draw so much so that y actual goes about the y that we find.
Which is right. So what are you trying to do? You are minimizing the y actual minus y.
Right.
Correct?
Yes. Sir. Yes. We're trying that
So you want to.
distance to delta very small.
So and what is y actual? Y actual is not a single number. So y actual there is n number of samples, and similarly y is also n number of samples. So what will you do? So you cannot take one sample. There are n samples, no? So you can do a summation of all the errors. How do you do it? You put a sigma over here. Okay, so now what is the problem with such a formulation? So this is basically what? The error. So let's say you have the error. So generally error, okay, with respect to sample, when you plot, okay, some part of the error may be positive, some, so let's say this is zero line. Some part, which means if y actual is more than y, then the error will be positive, and this is zero, and y is, I'm sorry. If the y actual is less than y, that part, so that particular sample, the error would be negative. So something like that. It would kind of distribute around your zero line. And when you take the sigma, what would happen is all this error ei over I will be very negligible, maybe close to zero, technically speaking. So just summation won't help because the sign of E can be positive and negative. So when you take the summation, the overall contribution decreases. So the standard way to do it, you add a square to it, which is the celebrated least square formulation. So this least squares try to bring in multiple things, okay? One is of course the double side. So your E is oscillating across a mean, which would be most likely zero, because error can be positive or negative. And if you just take the summation, overall contribution of all the errors would be very close to zero if you just put a sigma. But if it is a square, you are sure that the negative value will also be equivalently positive. And also one more important thing. So what is that? So what if you put square? This essentially means that, okay, today is very funny. Yes. So if you if you put a square, the other advantage is that the smaller error means lesser contribution to the overall penalty. So larger error means significant contribution. So what are we trying to say? Let's say if the error is, let's say your, what is error? Your y actual minus y. Let's say this value is close to 0.01. We don't care. This means that your y actual is almost equal to your y. You don't need to worry. You don't need to penalize them too much. Let's say your y actual minus y is 10, which essentially means that your prediction is off by the actual value by a magnitude of 10. So this has to be seriously considered. So if you take a square, which means that this becomes further smaller, and while this guy becomes very high. So by putting least squares, there are multiple advantages. Okay, one is of course the, so there are, in fact there are three things. One is the variability of error across the zero would be less because you are converting all the variable to positive. Okay, the second is the smaller errors will have lesser contribution and larger error will have larger contribution. And thirdly, numerically speaking, so see, uh, technically speaking, it is uh, so, so oftentimes the what I call the prediction would be, so if you consider the minimization, so if you consider, let's say, so you wanted to minimize, how do you minimize error? Of course you have to take the derivative of something with respect to that, which is the corresponding value and equal to 0. Square, okay, if you have the square, what would happen would be eventually, so which is d by, so let me also write it very precisely. So what we want to minimize the error square, okay? And what you really need to find out, in fact, it is not error square, it is the sigma of error square of I over all I. And what is that we need? The model parameters. Model parameter starting from beta naught to beta n. So how do you do it? So general, typical, how do you minimize the function? Tell me.
Equating the derivative to 0.
Absolutely. So let's say you have now you have to take derivative with respect to all these coefficients. So dou by beta naught with respect to ei square sigma of ei square equal to 0, so on and so forth. Dou by sigma of ei square with respect to dou by beta n equal to 0. Okay, so while doing so, okay, what is ei square? So now let's write it more precisely. Ei square is what? Sigma of y actual minus y square. And what is your y now? Sigma of, let me start writing y actual on the down just to make it more clear. And what is your y? Is beta naught plus beta 1 x1 till beta n xn. and you should put an I on the top because this is for the ith sample and your summation is for all I. Okay, and of course there is a square over here. And what would happen when you take, so this is E I sigma of EI square. So now let's take sigma of EI squared with respect to, let's try to solve it for each of this beta naught and equal to 0 and calculate, isolate beta naught and do it for all the other variables. EI squared, beta. So this is the gating principle of regression. So, but what is the problem here? So this is absolutely fine. So in this case, we have not just, so we start with, we have just started with beta 1, assuming beta naught is equal to, so if there is a beta naught, you add over here, beta naught plus. So now coming to what Ashutosh told, right, in matrix form and things like that. So this particular summation is technically very difficult to handle because there is a sigma, there is a multiplication. So what is the most compact way of writing this? Because what we eventually what we need is the total sum of errors between actual and the predicted. So a simple way is to write them in a very neat way of writing this is, let's say if I have y actual 1, okay, I'll make it as a matrix. Not, in fact, this is not matrix, this is vector, y actual n, okay. So this stands for the first vector, y. And how do you write? So let's say all your, let me write them all this data in a matrix form. It's like this, x11, x1n, sorry, x11 and xn1. I hope that's correct. Yes. Okay, so there is a mild confusion here. So the problem, what we are trying to do, we have used n for the total. So let's say the total number of data points. So we have, so we have written n here for the total number of parameters, and let's keep that. This is instead of n, we'll keep it m, just to keep it distinction. We have m data points and m parameters. So it is, so this become m data points and n parameters, which is basically your access. Okay, so now this is correct. So this would be now x1m and xnm, and you can fill in this. You cannot multiply this just like that because, so what you have to do is, so this is y minus, because what you really need is y minus, okay, and what we now require is beta 1, so assuming that beta not equal to 0 for simplicity, so beta 1 to beta n. So if you multiply row wise and column wise, you would get the y actual minus first y predicted. And if you look at the second row and second column, you will get the second element here and the corresponding. So this is the vector matrix form. Why it is vector and matrix? Some of them are vector, some of them are matrix. So again, just for simplicity, I will call all these vectors are capital Y. Okay, I will call big matrix are X. Okay, and this vector as B. I hope this is what it is written over here. Fine. So it would be Y minus X beta. This is what? This is just error vector. So I would say instead of E, I will like to write it as capital E, which is what? It's a vector of error from E1 to En. Okay, what we really need is what? E square. So there is, so if you are a vector, there is no notion of E square. It is just E transpose E. Because in the notion of linear algebra, the variable square essentially means that you take the transpose of two consecutive variables, which means y minus x beta transpose y minus beta. And you have to minimize this over all the beta to get your to get the model parameters. So there is no iteration as of now. We have to minimize this. Okay, so this is where we are. And when we solve this, I am just leaving you as an exercise. You can try it for a scalar variable and try to extend the same for the what we call vector variables. Okay, your beta value. Eventually, what? So, assuming leaving apart that this is matrix, you can just take one element and calculate this derivative with respect to beta, and eventually that would lead beta is equal to this x, okay, this x transpose x inverse into x transpose phi. So this is basically what is known as a closed form. This is homework, so you know how to do it. Homework. Just try doing it, and if you have some issue, get back to me. How do you do this again? Take the derivative. Equal to 0 for the vector beta. This is the celebrated closed form expression of regression. So, Ashutosh, take a look at, there is no iteration coming over here. This is closed form expression, which means that if you plug in this expression, you will get beta. What you really need is x and y, but this x and y, you have to assume that they are in this matrix form. X is the collection of all the data and y is the collection of all y. So somebody wanted to ask something.
So the iterative process could be finding the inverse in case we don't have a direct method to find the inverse, just in case.
Okay, I'll come there. So, as you rightly pointed out, the existence of inverse is a problem. So when do you think the inverse won't exist? There should be a physical reason also here.
Like if it's singular, so it would have a determinant zero inverse.
No, that is absolutely fine. That is a consequence, no? So when do you think such inverse doesn't exist? If you look at this, X, can you say?
I mean, how do we predict outright instead of it not being singular in that case?
No, there is a reason to it. How do you? So what is the reason for singularity?
Determinant is zero, or the rank matrix is not equivalent to the.
Okay, so you're saying about the rank. What is the so you're saying technically there is a rank deficiency, right?
Right.
Rank is not full rank. So what is the reason for not being a full rank?
Dependent equations, not independent.
So dependent equation. So you told till that time. Now you should be able to say.
So like we have replicating equations or duplicate equations instead of
No,
mutually
you
independent
don't.
equations.
Of course, it is replicating. Yeah, go ahead.
I mean, in that case, the rank would be less than the total number of rows, so grid inverse might not be
No,
possible.
that is true, but there could be one physical reason also to it, which is definitely connected with the rank.
I'm close, but can't
Can look
think
at it.
the right reason.
Okay. So see, as you rightly pointed out, rank deficiency, dependency of rows, columns can all happen. So one potential reason for that is, let's say, so what are all these factors? Let's say you're trying to predict composition, okay, and this X would be its related variable. Like you take a set of predictors. It could be temperature, pressure, maybe flow rate, or so on and so forth, and you stack them as a column. So this is the column of their n sample data. And as Ashutosh rightly pointed out, if there is a dependency, it could be row wise or column wise. It could be what you call the singularity could occur because of the dependency of the rows or columns. What would happen? So let's say if two of such physical variables are highly correlated, your x1, and let's say I'm going to write here one more thing, if I have space. Yeah, I think I have some space. X21, X2m. Let's say these two variables, which is, let's say, temperature and pressure of the same system. These two variables are highly correlated. So let me use the word. If multiple predictors are correlated, what would happen is that these two rows would have you can write one of them technically as a linear combination of the other one. That's what it means. They are correlated. So the correlation might help you to write one as a function of the other, which essentially means that these two rows would be kind of redundant equations in the form of a matrix. And eventually, when you try to do elimination, let's say the overall rank of the overall rank, if it's, let's say, m, it should have been m, it would be lesser than m. As a result, what would happen? It's a rank deficiency, and which is directly impacting the index. Is that clear?
Yes, sir.
Okay, so we are not going beyond this. So there are ways to iterative. I think somebody also told me there are iterative ways of finding the regression. Yes, it is. So this is basically due to this danger. So if this becomes the non-existence of the inverse or singularity, the existence of the singularity would help. So you might see people putting a hat over here. So it essentially means that these are estimated parameters from data. So these are estimated based on the data, which essentially means that if you take a new x, this beta might vary. So it is just an estimate, not a truth value. So that's why always statistics, all the estimated value would be given with a hat symbol. This is so if the x and y are different, or if it's a new set of x and y, your beta is going to be different. Or if you, let's say you have 1,000, if you have 1,000 entries, and if you just leave out 10 entries out of that and you recalculate your beta, the beta will be different. So it's essentially fully based on your data set that you have. So what we would have is, this is a strong function of the overall data. Okay, so now coming back over here. So this is essentially a fully data-driven mechanism. So any questions at the moment? Okay, so we'll also continue to some of the, so basically what are we doing? Technically, it is a fitting process. Fitting, or you might use it uh, because you have a function of x and beta. beta is your parameters, and you are fitting the beta to match your f of x, and this is y is equal to function of x of x comma beta, and there is some y actual there. You are fitting beta such that y is equal to y actual. That is what I call, in a nutshell, this is the process that we are doing. So you can also do the same thing. So this is fully regression, and you can also do the same thing to figure out the first order plus time delay transfer. So first order transfer function to get your time constant and the gain. So let's say you are plotting your the first order graph. It would eventually look like this, right? And y of t is equal to km times 1 minus exponential minus 2 pi tau. And what is the derivative of d by dt of y by km? So you have to take this guy over here, y by km, at t is equal to 0. So this would be 1 minus e raised to minus t by tau. So if you are taking derivative with respect to t, so it would be 1 by tau times e raised to minus t by tau. That is the derivative with respect to t. And at t is equal to 0, which essentially means that you substitute t over here, this term would essentially vanish, and 1 by tau is what you would get. So if you look at the slope at the so let's say if you plot, this plot is known as process reaction curve. Process reaction curve. Of course, this is a step response. So why it is called process reaction? This is the way the process reacts if you change the step, if you do a step change from point A to point B. So if it's a unit step change, this is the way process is going to react. That's why it is called as process reaction curve. And this is typically the first order response. There is no doubt about it. So what I am trying to say here, if you have the first order response, and if you draw a tangent at t is equal to 0, and calculate the slope, technically speaking. So you draw so this is the point, right? And you calculate the slope of this line, and the slope would be equivalent to 1 by tau. So if you need to get, so this is the simplest way. Okay, so you can also get it by means of what you call 0.632 times how the process varies. But one more way is just calculate the slope at the initial stage. And if you really are not sure about which one is correct, you take the average of both. You can calculate the 63% base, the time when the process becomes 63%, which is the tau in this station, and also looked at the slope and calculate 1 by tau, and from which you again calculated tau, and you take the average. So that would be more accurate value of getting the tau. Any questions at the moment? Please mind that we are only dealing with the data. There is no, so see, you are now fitting the parameter tau. So there is no mass balance, no heat transfer, no what you call transport equation, nothing. So this is the model structure, and you are fitting it. So this is fitting the model from the data fully. So, so this is for first order systems. And sometimes you may also have something known as first order plus time delay. How do you know if it is a first order plus time delay? Only way is just plot the graph again, y versus t. Your process takes slightly a what you call slow trans. Initially, it picks up slowly and it behaves like a first order from here. So what you could do is you can approximate this as a first order plus time delay, leaving apart this stable regime. So you may consider that the original process line would be like this. So how do you fit such model? The simplest way again is just to plot the graph, okay? And what you need to do is draw a tangent again at the point of inflection. Point of inflection is the point where the slope of the okay, so the slope of the line changes. So at the point of inflection, when you draw a slope or tangent and you draw it back, the point where it hits the x-axis and origin to that x-axis is the time delay. So this space would be the time delay. Okay, and of course this would go and hit over here as well, which is this is your overall y. This is y is equal to 1 or y by km is equal to 1, technically speaking. Or y, what is the type? It can be km or y by km is equal to 1, the ultimate value. And you draw from here and you draw it back. You draw a perpendicular from here back. And from that point to this point is your tau. This is another graphical way of finding out the tau value. So what you need here, you got your theta and also tau. Any questions? Okay, so in all the cases, we did not explicitly calculate k. How do you calculate the simplest? How do you calculate k? Huh? Someone? Change of output minus change of input. So you have recorded anyway input and output data. So see, what is your like in the previous case? Here you have the record of okay, 1, 2, 3, maybe n samples, okay, of y at y1 to yn, and you know what is the step change that is being done for input. So this is mu versus time. So this is the step change. So you have these two data available: rate of change minus rate of change of input minus rate of change of output, and that would always give you your k. Okay, so what is the problem with this particular method? So this is heavily dependent upon how do you draw the slope. The slope, let's say, unfortunately, you draw the slope like this, huh? The theta changes, your tau changes. So you can also draw slope like this at the tangent. So this is slightly subjective in nature for computing your theta and tau. So a better way again based on the graph would be is the following. What you have to do, this is your y of t as a function of y of t is km times e raised to minus t by tau, and you take logarithm on both the sides. Okay, and first of all, so yt by km, so you change it to yt by, of course, yt by km is equal to 1 by the yt is equal to km times 1 minus t by tau, yt by km, okay, is equal to 1 minus e raised to minus t by tau, fine. So 1 minus y by of t by km is equal to e raised to minus t by tau. Now you take logarithm on the both sides. So its left hand side would be ln of 1 minus yt minus km, and in the right hand side this exponential will be collapsed. When you apply logarithm, it would be just t by tau. Okay, so now let's say you have the last point, so which is the time at infinity, which is corresponding to km, and So you just substitute yt is equal to t is equal to infinity. Infinity means that your final value, technically speaking. So infinity does mean that your final value, which is k. So y of infinity minus y of t by y infinity is equal to e raised to t by tau. Now what you can do is, you can plug in t and yt and compute what you call each of these terms, and so so technically speaking, this should have been the case. Okay. So now when you have, so when there is a time, what you call dead time, so your process will not start at t. It will only start at t minus theta. So what you have is, if you plot y and ti, so when you plug in each of this and compute this versus t minus theta, of course, it could be a semi-log plot or a simple plot wherein you calculate ln and this. What you will get, the slope as minus 1 by tau. This is another way of doing it. So there are multiple ways. One is, of course, directly using the what you call the point of infection method. Here, of course, we have not used anything. You computed these two parameters and plotted, and eventually, what you are getting is the time delay. So if this method may be slightly better because you are not using a single point. You are using a collection of points here. Collection of points. While here it is a single point method. Why your point of inflection is a single point. So that point, when you draw this inflection point, is your result is highly dependent upon that. So again, graphically. Okay, and of course, this is all for the first order system, and you can also do the same thing for the second order systems and higher order systems, of course. And when the order become more and more, your results, like what you call the more difficult to kind of compute them graphically. So up to second order it is okay. In the second order calculation is second order computation of, so in second order you have to compute, of course, zeta and tau2 parameters. K again is y2 minus y1 by u2 minus u1. So there is no difficulty to find k. The other two parameters are theta and tau. One particular method that people use, of course, is basically known as Smith's method. In Smith's method, what you will do is, okay, so check you the so we will show. So this particular graph is being used in Smith's method. What as a reckoner? So you will use this graph. It's like a heat exchanger table. You compute something. So what you will do is, you compute the point when the overall process becomes 20%, which you call it as T20, and you also compute when the process becomes 60% as a total value, which is known as this is known as T60. Okay, so let's say that value is, let's say, 0.4. You compute the ratio of T20 and T60. So your x-axis is the ratio of T20 and T60, and let's say that value is 0.4. Okay. To get theta, what you have to do is, you just need to draw over here, okay, and project over here. So if that if T20 by T60 of that particular process is 0.4, means that it's mostly a critically damped process. Your theta is very close to 1. Okay, so now what is, so you have got your theta. Now you need to get your tau. So if for the tau also, you have to just draw this over here. And if you draw, and when when it hits the y-axis, what you are going to get is C60 by tau. So you know already the value of C60 because that's what you have used here. Then you can isolate the tau. So this chart is very helpful. This is a standard chart. This could be used for fairly all possible systems for computing theta and tau for second order system. So you come to, so of course it is slightly empirical in nature, which means that you are not using any other method here. It's mostly based on the chart. So there should be some errors, but fairly by and large, most of the processes, you should be able to figure out the theta and tau from each of this. Okay, so let's say if it is an overdamped system, further, an overdamped system, you should be able to isolate. So if it is an underdamped system, you shall be able to write the transfer function like this. But if it is an overdamped system, you generally people write the transfer function as k by tau 1s plus 1 and tau 2s plus 1. E raised to minus theta s, of course. So getting just tau and theta is not really sufficient. You also need to identify the individual tau 1 and tau 2. So for overdamped system, this expression is good enough to figure out independent tau 1 and tau 2, which is a function of tau and theta. Any questions here? Any questions? Anyone? Are you all following, or is there any issue?
Sir, it's
Go ahead.
no, sir. I said that it is clear.
I can hear you. Yes, Visuddha, go ahead.
Sir, I was just saying that it's clear.
Your voice is cut.
Sir, it's clear, good to go. So no queries regarding that.
Okay. So we have now how many minutes? Okay, so we shall quickly do this and stop for today. So these are so see.
So
So
one
models
clarification that we
and
had regarding the minor syllabus. Could you please take the syllabus till notes 5 because we won't have time to do the tute for this lecture 6. Would that be possible?
no. So we have done so the tute. So last tute we had done some examples up till here.
Right. So
First
could you
order
please
plus time delay model.
tell it up till now so that we can focus on the part done till now? Like the quiz was a
No,
model.
no, I'll tell you. So your the minor syllabus will be till the slide number 8.
The entire one.
No, so this step, this notes till slide number 8.
Okay, till slide number 8 for overdamped system. This one.
Because these things. So so the last question in the tute was something related to fitting first order models and fitting first order plus time delay model. So this has been already covered in the tute slightly early though by explaining this.
Also, note 6 haven't been uploaded, I think.
So that's my mistake. I will upload it right now.
All right, sir. Thank you.
Okay.
Got it, sir. Thank
Okay,
you.
so in that connection, so in that connection, we may either take the neural net now because anyway, this is part of the short sensor. So Friday, anyway, I am not planning to take the class. It could be either a doubt clearing session or just a free go, whichever you would like to, whichever way you want to do. What is the best way, Ashutosh? You can tell me. Either we shall move the doubt clearing session from afternoon to morning and leave the afternoon free, or if you want the whole thing to be free, it's up to you. If you want to study in that mood.
So I'll have to
You
ask the
can
class
drop
on
me
this
an email.
because I understand that attendance is an issue. So we'll have to ask the class on what their opinion is. Probably after the minors, once they get their scores, it might lead to more motivation for the entire crew to study, including myself.
No, that's fine. So I will upload the notes. What I am trying to say is so we may be able to use the Friday class, because I don't want to teach anything beyond this, because this will also go to anyway into your second module. Sorry, post minus syllabus. So I don't want to now teach it and keep it there. But so either we should do a review on Friday, or you would. So anything up to, I am fine. So I am not going to take anything new on Friday. That's what I am trying to say.
So a review would be good so that everybody gets a hang of what's going on, and they have a heads up around the minor syllabus.
So you are saying a review class is good enough?
Oh yes,
I
so
think
it's got doubts.
Yeah. So that's fine. So that should be okay. So this is what. So maybe what's the time now? 11:54. So okay. So we will just start this up. So see, till now we were all. So see, we talked about linear regression, and there are of course non-linear regression. So see, what are, so these are all what fully data-driven models. So, so what is the difficulty that one would face? If you have more, if your data become more complex, of course, the linear models like simple linear regression might not work. And as we told, this is all fully data driven in the sense that it's completely dependent upon data. There is nothing, there is no physics coming in. You see, of course, barring about the first order plus the intellectual, or just look at the regression. There is no physics coming in. It is just fully based on the data. You are figuring out the model parameters that explains the minimum error, which is your y minus y actual sum square, which is again written as the matrix. Okay, so the problem in the case is when the data become more and more complex. Okay, you also need to figure out the models that are able to model such kind of data, because this is fully data driven. You don't have any other means to connect. Thus, so this over the time has led to models like neural nets, which is celebrated at the moment. There was a time when the neural nets were fully ignored by people, because now they kind of did a what you call super makeover, and now known under very fancy name deep. So, so this, you see, the neural nets were in 1970s. Huh? Then it picked up in 1990s. There was a larger fraction of people used to do neural nets. Then between 1919 to let's say 2010, there was a big time dip. People say this is like a junk. You cannot use this. You won't be able to get anything out of it. This was primarily because of the see, difficulty to handle large data. Because your hardware, so even the algorithms were mature enough, your hardware were not mature enough to deal with such large data. There was no cloud, there was no what you call storage worth petabytes and things like that. So eventually, the big part of the data got ignored, and that kind of took a big dip on the neural net. Okay, so then post 2005, the peripherals were really good. Like over the time, that growth was phenomenal. Your data storage capacity increased, the data processing capacity increased, which essentially means that your processors were good enough to deal with the data. And also what you call as parallelization. So this is this parallel computing emerged, which means that you can parallelly process various chunks of data. Okay, so now at that moment, this neural net again took their rebirth. It was again in 70s, then went down, severely down. Because now they were, so see, this was actually born much earlier than it needed. So at the time, the technology, the hardware technology were not mature enough to deal with such complex things. Then, when it of course did a rebirth in 2010, of course it required a rebranding because again it started using neural net. People won't understand or people won't use it. Then of course, yeah, computer science people are really good in branding things, so they rebranded it as deep neural net or aesthetically the deep learning. Deep learning is basically what just learning in neural net that has sufficiently a large size. So, okay, I'm not going to talk into the detail how a neural net works. I think many of you might be knowing. So you have a lot of inputs, and this inputs will be processed, okay, by means of weights and biases to get the output. And each of these layers are called hidden layers. Sorry, and each hidden layer will have an activation function. This activation. So each of these activation functions are non-linear, while weights, all of this weight. So if the inputs are multiplied with the weight, then they do a summation, and at each of the hidden layers, they would be operated over an activation function. And this procedure is followed until you reach the output. And you may have multiple hidden layers or single hidden layer depending upon the problem. If there are multiple hidden layers, you call it as a deep network. If there's a single hidden layer, you call it as just a simple neural net or whatever. So we'll stop it over here, and we'll see you on Friday. Okay? And I'll upload the notes. And if I forgot, I not, of course, so just can drop me an email. Okay?
Right, sir. It's all right.
Okay, guys. Bye bye.
Thank you so much.